Hello everyone, today we're going to discuss about AC circuit containing inductance only. Sometimes this topic is referred to as a purely inductive circuit. It's a circuit which has got only an inductance in that particular circuit. So in an inductive circuit, in a purely inductive AC circuit, the current lags the applied voltage by 90 degrees. It means therefore that in an inductive circuit, the angle between the current and the voltage are apart by 90 degrees. That is why we say it lags behind. And remember, it is the voltage which is actually ahead of the current. That is why we say current is lagging, because the voltage is ahead by 90 degrees. But like we have said before, in a series circuit, current is taken as the reference. Whenever you are drawing the phasor diagram, the current is always taken as the reference phasor. Therefore, it means the current is drawn on the horizontal scale. Look at this phasor diagram. This is our phasor diagram, and this is our circuit diagram. So in the circuit diagram, we have said that the voltage and the inductor are connected in series. That is why we say this is a series circuit. This is the voltage source, this is the inductor. And because it is a series connection, current is the same. Because current is the same, therefore whenever you draw a phasor diagram, current is drawn on the horizontal scale. Once you draw current on the horizontal scale, and we have said voltage is leading. In an inductive circuit, voltage leads current. In other words, we say current lags behind the voltage. So because the voltage is ahead by 90 degrees, so you draw it vertically. The voltage, because if you measured from the current to the voltage, the angle between them will be 90. That is why we are having 90 between the voltage and the current. So this is the phasor diagram of an inductive circuit, and this is the circuit diagram. When you are drawing the waveforms, whenever you are drawing the waveforms, what you will do is, this one is taken to be the time, because we are drawing time against the parameters. Current is always taken to be the reference. The current will begin from 0, because current is taken as the reference. So draw that waveform like that. Now, we have also said that the voltage is leading by 90 degrees. So at the top, remember the current is taken as 0 on the horizontal scale. That is why we have started from 0. But now voltage starts at 90. That is why we are starting at the top. So it moves down like that. So whenever you are drawing those waveforms, those are the key points to note, that the current waveform is taken as the reference beginning from 0. The other one has to stop at the top, leading. If it was lagging, you start at the bottom. But because the voltage is leading, you start at the top. We now look at an example. A coil has an inductance of 40 millihenries and a negligible resistance. Calculate the inductive reactance and the resulting current if it is connected to 240 volt source or supply. So what is very important there is to know the formulas. We have said before that an inductor offers inductive reactance. Inductive reactance is given by, inductive reactance is denoted by XL. Remember we said X denotes reactance, but when you want to become specific, you need to introduce a subscript below this letter to specify the kind of reactance that you're talking about. So if you put XL, the subscript L of course says that it is a inductive reactance. If you put C as the subscript, then it will be called capacitive reactance. So the subscript will specify the kind of reactance you are talking about. So inductive reactance is given by 2 pi FL, where we know F is the frequency of the source of supply and L denotes the inductance, but this inductance has to be in henries. Henries. If it is in millihenries, of course, you need to change it to henries. So you substitute the values. Remember, in the equation we have been given 50 as the frequency, we have been given 240 as the voltage. So you need to substitute, and we have also been given 40 millihenries as the inductance. Remember, I told you you need to work with henries, so you have to change this one to henries. So you need to multiply this value by 10 power negative 3, or you need to divide it by 1000. So we have written 2 pi, replace f with 15, L is replaced by 40, but you need to change it to henries. That is why we are multiplying by 10 power negative 3 to change it to millihenries. After that, you will get 12.5 as the inductive reactance. Inductive reactance is 12.57. So once you get the reactive reactance, remember current is given by voltage over reactance. The same way we do it when you want to get current, which is given by voltage over resistance. In this case, we talk about reactance. So it's given by voltage over reactance, which is 240 divided by this. It gives you 19.093 amperes as the current that is flowing in this circuit. We move on to another circuit whereby now you have a resistor and an inductor. Remember, not all inductors are purely inductive, meaning the coils could be having some form of resistance. So to cater for that resistance, that is why we have to discuss a circuit which has got some resistance and inductance. Not necessarily that we are connecting a resistor alongside the inductor, but the inductor itself has got some form of resistance that we need to consider. So that is why we are discussing RL series AC circuit. In an AC circuit containing inductance L and resistance R, the applied voltage V is the phasor sum of the voltage across the resistor and the voltage across the inductor, denoted as VR and VL respectively. And thus, the current I lags the applied voltage V by an angle phi lying between 0 and 90. Remember, in a purely inductive circuit, the voltage and the current are out of phase by 90 degrees. But the moment you start talking about a resistor being connected in that circuit, or the inductor having some form of resistance, the angle between the voltage and current will never be 90. It will be a value less than 90, but not less than 0. So the value will be between 0 and 90. So the moment you increase the resistance, of course, the value of the angle keeps on reducing. In an AC series circuit, the current is common to each component and is thus taken as the reference. That we have said that in a series circuit, current is the same across the components. So meaning, if you have this is our circuit whereby the resistor and the inductor are connected in series. Because the two components are connected in series, then it means the current across the resistor and the current across the inductor will be the same. That is the reason as to why current will be taken as the reference when we are drawing this particular circuit. So we can look at it. You can now see we have said current, the voltage. The current is actually drawn on the horizontal scale. We have also said before that in a purely resistive circuit, voltage is in phase with the current. That means that the voltage across the resistor will be drawn alongside the current. That is why you can see the voltage across the resistor is also plotted on the horizontal scale, because for a simple reason that current is drawn on the horizontal scale and the voltage is also in phase, meaning they are just moving on the same line. That is why we have presented the voltage along that side. We have also